Hello everyone, I hope you are doing well. So in this video, we're going to discuss Geeks for Geeks problem of the day, and today's problem is minimum distance between two given nodes of a binary tree, right? And the problem is very straightforward. It says that we have been given two different nodes and we have not actually been given the nodes, we are just given the node value, right? The input to us will be given in terms of node pointers, and as you can see, this is the node pointer and the other inputs are in terms of integers. Now we have to find the distance between these two nodes. The very first thing that you must observe in this particular problem is the question says minimum distance, but if it is a tree, there will be exactly one simple path to go from A to B, right? So from 2 to 3, you'll always have one path, and you cannot have multiple paths. If you have multiple paths, it will become a graph, right? This is the very first thing. Now one way to solve this problem is to convert this whole tree into an adjacency list and then easily solve it, right? That is the most simple problem. And the other way can be using a concept which I was also talking about yesterday, but we'll finally discuss it today. So the concept is called binary lifting, and with the help of binary lifting we are going to find the lowest common ancestor, right? So let me quickly explain you what these two different terms mean, and then we'll figure out how we can use them to find our answer in this particular case, right? So the first step will be understanding these terms and their use cases. The second step will be having a look at my template. The third step will be having a look at the final code for this particular problem, so that we can understand how we modify the template to fit into this particular problem, right? So let us first understand what is binary lifting. Binary lifting, I also talked about this particular thing yesterday, but I did not discuss it. I just said that this is a topic that might help you solve the previous problem, right? So binary lifting basically helps us to find the xth parent of any node, right? How does it help us to do this? It helps us by finding, let's say, these values, the value of x, right? So it does not have all the direct parents. For example, this is also a tree, right? So let's say this chain is of size 10 to the power let's say 8, right? So if you want to find the 10 to the power 8th parent of this particular node, you will have to traverse the whole list. This is not feasible at all, right? So what we instead do is we do not store all the parents of any node, we store the parents in powers of 2, right? So let's say we have a node, let's say I generally call this vector up. So vector of node up node 0 will store the 2 raised to power 0th parent of node, right? So this might feel a little bit jarring right now, but with time you will understand this. Now up of node of 1 will store 2 raised to power 1th parent of node. Similarly, up of node of 2 will store 2 raised to power 2th parent of node, right? So what is the advantage of storing these powers of 2? Now let's say you want to find out the, let's say, 15th parent of any node, right? So how can I represent 15 in binary form? So it will be, I guess, written like 8, 4, 12, 13, 14, 13, like this, right? So what you can do, you can find the 2 raised to power 3th parent of current node. Then you can find its 2 raised to power 2th parent, the next node you have find. So let's say P is equals to up of node of 3. Now you can find P2 is equals to up of P of 2. Now you can find P3 is equals to up of P2 of 1, right? This way each time you are choosing one of the bits. Now you would obviously not write P1, P2, P3, it will be just in a while loop or some kind of for loop, right? But just to make you understand that you can separate these powers of 2, because what is 15? 15 can also be written as 2 raised to power 3 plus 2 raised to power 2 plus 2 raised to power 1 plus 2 raised to power 0. So I separated these powers of 2 and wrote them separately. So basically this is how this up vector helps you to find any parent of any of these nodes. Now the question is, how do we actually construct the up vector? So it's more like a dynamic programming approach, right? So let's say you want to find up of, let's say, node y, right? For each node you want to find up of y, right? So how can you form it? If you know up of node of y minus 1, then you can probably find it. Let me discuss this how. So let's say these are the nodes, right? So from here you want to find out its fourth parent, right? 1, 2, 3, 4. You will know that the topmost node is its fourth parent, but you don't know it yet. So what you're going to do, you have fourth parent means this y value will be equal to 2. So y minus 1 was 1. That means you have already calculated everyone's second parent. So its second parent is this one, right? This one. Now what I can do is, I can find the current node's second parent, and from there I can again find its second parent, right? So instead of writing directly 4, I just wrote it as 2 plus 2. As I've already calculated the second parent of every node, then I can easily calculate the value of 4, because let's say this is current node is y. So I calculate p is equals to up of, so this is x, right? So x of 2, then I can find up of x of 2 basically means here 2 raised power 1, and then here up of x of 2 is equals to up of p of 1, right? So this is the initial node x, this is 2 raised power 1. That means I want to find a second parent of x. Now the fourth parent of x is here, and this is 2 raised power 2. So the fourth parent of x is equals to the second parent of this newly found node that I found as the second parent, right? So basically this is how you can divide this original 4 into 2 plus 2, and you can find any parent. So to find any parent y or 2 raised power y for each of these nodes, you need to calculate y minus 1. Now eventually you can reduce it to the base case, and then you can always find 2 raised power 0, and that is 1. Once you know 2 raised power 0, you can find 2 raised power 1. If you know 2 raised power 1, you can find 2 raised power 2. If you know 2 raised power 2, you can find 2 raised power 3, and so on. What is 2 raised power 0? It will be the direct parent of each node, which we normally know while traversing the tree, right? So I'm just trying to give you an overall idea. I know this is not the best explanation of this particular concept. It's rather like a medium to hard concept, not very simple to grasp. So I'm just trying to give you an overall idea so that you can understand or get a slight glimpse of what this binary lifting is, right? Now if you want, I'll suggest you a very good video. It's by Ericto. You can find out this video on YouTube. So you can also search for binary lifting or finding the lowest common ancestor. He has made both of the videos. Both of the videos are amazing. So you can watch those videos as well if you don't understand it here. Now we have understood what is binary lifting and what does it help us. It basically helps us to create this up vector from which I can find any parent of any node. Now our task is to find the lowest common ancestor. Let us understand how this lowest common ancestor will help us. Let's say I want to find the distance between these two nodes x and y. So what I do is I find this particular lowest common ancestor. What is the lowest common ancestor? So what I'm going to do, I'm going to go towards the root from both of the nodes, right? The first node which exists in the path of both x and y is going to be my lowest common ancestor, right? So basically if I start going from my node to the root node, the first node which will exist in the path of both x and y is going to be my lowest common ancestor for x and y. How does this help us to find out the main answer, or how does this help us to find out the distance between these two nodes? You will always observe that whenever I want to go from x to y, in case of a tree, I told you that there is only one path, and that path is going to be from the lowest common ancestor. This is for sure, and this is the hard code rule. You can identify this by going through a few test cases or by going through a few observations, but you will always realize that, let's say you want to go from x to y, you will go towards the root, you will reach the lowest common ancestor, and then you will start going towards y, right? This is always going to be the path. Now, if you know this particular lowest common ancestor, how can you find out this distance? What you can do is you can take the depth of x. So you can take the depth of x. Then you can take the depth of y. Right. If you add these two terms, you will see that this distance was added once, this distance was added one more time, and this distance was added two times. Right. So let me just mark it. This is added one time by this depth of x, and this distance is added one time by depth of y, but this distance is added by both of them, and so I need to subtract this distance. What is this distance? This is the depth of my lowest common ancestor. So minus twice of depth of LCA. Right. This is how your LCA will help us to find the distance between x and y. But now the question is how to find the LCA. We are going to find the LCA with the help of binary lifting. Let us see how. I'm just going to give you a very simple example of doing this. This is not going to be enough if you are studying for the first time, but this is going to be enough if you're doing it for a revision. And if you're studying it for the first time, Erecto's video is the way to go. I highly recommend you to watch it. Right. So what we generally do is we find out the distance between these two nodes. Right. Distance between the depth of these two nodes x and y. Here you can see that the distance between or the difference between the depth is dx, that is 2. Right. So my first task is to make both of them at the same level. Right. So what I can do is I can bring y to the same level as x. Right. Now how we can do is we have first found out the difference between the depths. Right. That means y needs to move 2 times upwards, or y needs to go towards the 2th parent of y. So I can make y move here by finding out up of y of 1. 1 in this particular case because it is the 2th parent, so 2 raised to power 1 is 2. Right. Now if it was a complex number, so you will have to do this. Let's say this was 3, so p is equals to up of y of 1. Then your final is equals to up of p of 0. This is how it is going to be like. Right. So because why is this like this? Because this is 0 and 1, we have both the powers, so we have to do operations for both of them. Normally you would do this in a for loop. Right. Once both x and y are at the same level, we are going to move x and y together upwards. Now if you find the, let's say 1 2 3, right, 1 2 3. So this node, since both x and y are at the same level, this particular node has a distance of 3 from both x and y. If I move it 3 upwards, then I would have missed the lowest common ancestor. So I would move it upwards in such a way so that I do not miss the lowest common ancestor. This is going to be my goal, right? So I only move it up till here. You will see in a while how do we do it in the implementation, but the idea is to move both x and y together such that they do not cross the lowest common ancestor, they remain below the lowest common ancestor, right? So this is how we are just going to move them upwards. Now once we move them upwards, we are going to reach this node in both of them, right? This particular node in both of them. Once we reach this particular node, my answer is going to be, let's say my x has reached here and y has reached here. My answer is going to be up of x of 0, or I can also return up of y of 0. This is how I find my lowest common ancestor, right? Now I know this is again a not very simple problem, and this approach is relatively hard than any other concepts, and it is difficult to understand, especially when you study both of these things together, binary lifting as well as lowest common ancestors, right? But this is going to be very helpful. Again, if you don't understand it, Ericto's video is the way to go. Also Code and Code, so there is also one more channel, Code and Code. It has also uploaded the videos regarding the same topic, and they both have explained this particular concept in detail. Due to the nature of these problem of the day videos, I cannot go into depth of these topics, and I have to make these videos very quick. That is why I cannot explain the topics in detail here, and I am recommending you one more channel. This was a good revision, but not a good enough explanation for the first time, I know. So let us just discuss how we can solve this particular problem. I'm just going to switch to my template first and then show you my code, right? So we'll study this part first. I'm just going to take this. So you see what I do is, the very first thing I'll do is, I create value of n. This is going to be the maximum number of nodes, right? So remember, this problem is made for an adjacency list of graph where every node is determined by an integer. Assuming that there are 10 to the power 5 nodes, I have created this. Now, since I need 2 to the power ith parents, then I can take log 2 of n and just add 1 to it just for safety purpose. So log is basically representing all the powers of 2. So if I have a number n and I take log base 2 of n, I can get all the powers of 2, right? So I'll get an upper bound of what I need to store in the second half. Now I create a double dimensional vector of size n cross log, right? Now I also create a depth vector of size n. So n is y, the number of nodes. Now I call the setting parents. Now this is going to receive a node, this is going to receive the parent, this is going to receive the current depth and the adjacency list. Now up of node of 0 is always going to be my parent, right? I told you about the base case. So how we solve this? We set the node of 0, that is the immediate parent of my node, as a parent. This I can obviously get through the traversal because I am receiving the parent here. I set the depth of node as d. Now I am going through all the different powers. If up of node of I minus 1, remember I talked about computing I. So before I need I minus 1, right? So up of node of I minus 1 is not minus 1 yet. Then I am going to set up of node of I as up of this value, which is up of node of I minus 1, and then again take its minus 1. So basically if I am here, right, if I want to calculate the fourth parent instead of calculating it directly, so let me set the marker. If I want to calculate the fourth parent instead of calculating it directly, I can calculate the second parent of its second parent, right? I take this node, calculate its second parent and take its second parent. This is exactly what I have tried to do here. I have taken the node, taken its second parent, that means I minus 1th parent, and from it I have taken the I minus 1th parent. This is how you can calculate the parent for I, right? Now I'm just going to go through all the children and again call the same function on them. Since this is a tree, I do not want to go to my parent. So if child is not equals to parent, I'm going to go to child. The new parent will be node, the distance will be d plus 1 and adjacency list will remain the same, right? Now let us have a look at the LC function. This is also very simple in code. The concept is a little bit difficult to understand, but once you understand the concept, the code is relatively simple. So as you can see, what I've done here is, first of all, I've compared the depth of x and y. Why this particular step? Because I would want a standard that always depth of x should be greater than depth of y, right? Or depth of y should be greater than depth of x. It can be any of these ways. In this template, I just chose the first one to make everything all standard, right? So I always want that x is at a greater depth than y. So if depth of x is less than depth of y, I am going to swap both of them. Now I calculate the value of dx, that is the difference between their depths. Now with the help of this dx, I am going through all the possible powers of 2. If dx right shift I and 1, that means if the ith bit is set in dx, then I am going to move this particular x upwards 2 to the power I times. Eventually what will happen is I would have moved x upwards dx times, right? Total number of dx times I would have moved x upwards so that x and y are at the same level. Now if they are at the same level, they might be the same node or might not be the same node, because you see that these two x and y are at the same level but different nodes. X and y can also be like this at this particular node and be the same node as well. So if both of them are same, I'm just going to return both of them, right? Now if they are not same, that means I still have to move them upwards. So I'm figuring out all the powers starting from log minus 1 till greater than minus 1 and doing I minus minus. If up of x of I is not equal to up of y of I, that means if they are not reaching the same node in this particular power of 2 to the power I, that basically means, I already explained, if they become same, that means they have crossed the lowest common ancestor. So only if they are not same, I am going to move x and y upwards both 2 to the power I times. Once I move them upwards, they will be in a situation such that they are very close to the lowest common ancestor, but they have not reached it yet. And those will be the just immediate children of the LCA. So now I'm just going to return the direct parent of my X, or I can also return the direct parent of Y, right? So this is how you find the LCA. Now once you find the LCA, finding the distance is very, very simple. So let me show you my code, what I've done here. I first of all call the setting parents function. Now the first part is going to be the root, the second part is going to be an integer parent, and the third part is going to be the depth. So I had to define these up and depth vectors a little differently, primarily because the integer values here are not fixed. You can see it can go up to 10 to the power 9. So this is something we cannot handle directly because the first part has to be an integer, right? So what I did was, instead of using a double dimensional vector, I am using a double dimensional map, right? And I've also created a default vector for each of these nodes, right? You'll see in a while what it does. So I'm just going to my setting parents function. If my node is null pointer, I'm just going to return. Otherwise, I'm going to take the value of the correct node. Now up of value is default. This basically means initially what I did was I initialized all the values with -1 in this up vector. But since now I have a map, I have no way of initializing these values to a default value, right? It will do whatever it wants. So whenever I reach a new node, I'm going to initialize it with this particular default vector so that all the values for this node are -1. Now up of value of 0 is going to be a parent I'm receiving an integer, but node I'm receiving it in node pointers. That is why I have to convert it into value first. Now I set the depth of value as d. Again the same part, this is very simple. Now setting parents to node left and node right and passing the node data so that this becomes a new parent and d plus 1. Now here everything is same, both x and y are everything same. Thus a setting of function is a little bit different. Once you set up these functions, you can get the LCA by get LCA of A and B, and your answer is going to be depth of A plus depth of B minus twice of depth of LCA, and then you can just return your final answer. So I'm saying it again, if you had any trouble understanding this particular concept, then you can watch Ericto's video. It's very amazing, and this concept is a little bit difficult to understand. So even if you don't understand, you don't need to worry about it, and take your time. And that's it for this video. Let me just quickly submit this so that you can understand this particular problem works. So you see this passes all the test cases. This solution is absolutely correct. I hope that you guys were able to understand the solution. If you guys did, consider dropping a like on this video, and don't forget to share thoughts in the comments, because your engagement with this video really helps the YouTube algorithm to understand that this video is actually helpful for you, and if you're able to reach much more people like you who want to keep solving new problems. So that is it for today. Till the next video drops, keep coding, stay safe, bye bye.